For the step response tuning, first add Kp until the motor overshoots and oscillates about the commanded position. Then add Kd to stabilize the motor and dampen the oscillations. Lastly, add Ki in order to drive the steady state error to zero if body forces such as gravity or friction are affecting your system. Not all systems need Ki. The performance design goals for the step response vary between applications. Some may tolerate more damping, some may tolerate some oscillation, some overshoot, but generally speaking, your goal in tuning these gains is several-fold. We want to minimize overshoot, which is the amount that the motor overshoots the commanded position. We can do this by adding Kd. We also want to minimize the rise time, which is the time the motor takes to reach the commanded position. A smaller rise time means a quicker response. We also want to minimize the steady state error, which is the difference between commanded and actual position once the motor is at rest. Ideally, your steady state error should be zero. We also want to minimize oscillation. The motor should not oscillate too rapidly or drastically because this can often damage the mechanics in most systems. You can minimize oscillations by adding Kd. We also want to get the best possible bandwidth, which means the fastest possible response, without destabilizing the system. This is done by setting Kp as high as possible without producing too much oscillation. Lastly, we want to eliminate quantization noise by having an optimal value of Kp and Kd. Quantization noise can appear in the system when these gain values are too high. So now let's look at some example conditions. The diagram in the top left corner shows a step response that overshoots and oscillates about the commanded position. You should try increasing your Kp from 0 until you reach this condition. After you achieve a good bandwidth, which is shown at the bottom of the step move plot, you can start damping out the oscillations by adding Kd. The bottom left corner shows a response that is too damped and is therefore sluggish. It does not even reach the commanded position until the end of the step time, and its rise time is unsatisfactory. To improve this kind of response, either add Kp or decrease Kd. The top right corner shows a response with a position offset between the actual and commanded position. That is, the motor settles at a location either above or below the target position. This can be caused by DAC offset. You can eliminate DAC offset by performing the DAC calibration, which is the process of ensuring that the amplifier outputs zero current when you command zero current. See the motor setup tutorial videos if you're not sure how to do this. However, if you have properly calibrated the DACs or the ADCs, this offset can be ameliorated by first trying to add Kp until the offset is eliminated. If that does not fix it, try adding some Ki. The bottom right corner shows the physical limitation of the system. If you see this kind of response, you may have maxed out your system's capabilities, but it might also be possible that you just need to add more Kp, so try that first. This sort of shape can occur if you subject the motor to a move that's too difficult for the motor amplifier and load combination. The magnitude of the gain you need to use will vary depending on your system. The higher the resolution your motor's feedback is, the smaller the gains will need to be. Note that when you are issuing the step move, make sure you are plotting the servo command on the right axis plot. If you see a saturation of the servo command at the beginning of a move, you have reached the maximum output command as determined by motorx.maxDAC, which is a structure that limits the servo command for the safety of your motor and amplifier. In this case, adding more Kp will not improve the step response's performance. You can tell if the servo command is saturating when you see a sudden flat spot in the servo command, like what is shown in this plot. Now select the Parabolic VEL period tab to access the Parabolic Move. The Parabolic Move helps you determine how well your motor can track a constantly changing trajectory. It commands a positive, parabolically shaped speed to the motor, and then commands a negative speed trajectory of the same shape right after that. The shape of the acceleration is naturally triangular, like two ramps meeting. It's important to select a move size and move time that simulates a move that you would expect the motor normally to make. If you tune for a worst-case scenario, that is, a difficult move, then the tuning would also work for easier moves. The tuning goal for the Parabolic Move is to get a following error curve with the smallest amplitude possible, oscillating about 0. Note that a great starting point for KVFF is to set it exactly equal to KVFB. Typically, only small variations in KVFF need to be made thereafter. The procedure for tuning to the Parabolic Move is to compare the motor's following error with the commanded velocity and acceleration shapes. You can choose which one to plot at the bottom right corner of the Tune window.